Now that we're done with performance, this is a good time to do a brief refresher on weight and balance. Calculating weight and balance is a critical part of any flight. Knowing that your takeoff weight is within limits or how fuel burn will affect the center of gravity are some of the important considerations. Fortunately, helicopter weight and balance is calculated just like airplane weight and balance. You'll need to be able to calculate whether the weight and center of gravity are within limits, the location of the CG, and how adding a passenger or how fuel burn will affect the center of gravity. Weight times arm equals moment. Use this formula to compute both the left and right moments. The pilot weighs 140 pounds. Multiply that by 13.5, and the pilot moment is 1,890. The co-pilot, sitting on the right, weighs 180 pounds. Multiply that by an arm of 13.5 inches, and we get a moment of 2,430 pound-inches. Second, find the difference between the moments. This gives us the offset. Take 2,430 pound-inches from the co-pilot on the right and subtract from that 1,890 pound-inches from the pilot on the left. That gives us 540 extra pound-inches on the right side. Third, find 540 pound-inches right of zero on the bottom of the lateral offset moment envelope graph and move upwards until you intercept the 1,800 pound gross weight line. The point where the two lines intersect lies within the envelope. No action would be required. The lateral balance is okay. How you load the helicopter will affect its flying characteristics. If you load the helicopter so that the CG is located aft of the allowable CG limit, it'll be difficult, if not impossible, to lower the nose if it should pitch up. If you think about it, this makes sense. There's too much weight in the back, causing a tail-low attitude. There won't be sufficient forward cyclic displacement available to push the nose down. This could be especially problematic in gusty winds in high-speed flight where it's necessary to maintain a nose-low attitude. Similarly, if you load the helicopter so the CG is located forward of the allowable CG limit, there's too much weight in front. This is probably most dangerous when the engine fails and you have to auto-rotate. The helicopter is in a nose-low attitude and there may not be sufficient cyclic control to flare properly to land. Again, the calculations for weight and balance are not difficult. You just need to make sure that you don't make any arithmetic mistakes and that you read the charts and graphs correctly. Okay, we're moving right along. It's time to analyze some typical helicopter maneuvers. We'll take a look at surface taxiing, quick stops, confined area operations, pinnacle and ridgeline operations, slope operations, and running takeoffs and landings. So enough of the classroom. Let's take a look at the actual maneuvers. A helicopter with skids for landing gear usually hover taxis several feet above the ground. Taxiing while the helicopter is in contact with the ground is called a surface taxi. Usually only wheeled helicopters surface taxi. However, even helicopters with skids will surface taxi in some situations, such as when rotor downwash in a hover might cause damage to other aircraft in the vicinity, or when the helicopter's gross weight is high. To surface taxi correctly, initiate movement with slight upward collective pressure, maintain heading control with the anti-torque pedals, and ground track with the cyclic. Hold the cyclic into the wind as necessary to correct for drift during crosswind conditions. Use the collective to control starting, stopping, and the rate of speed. The more collective that's added, the faster the helicopter will go. You know, there probably isn't a helicopter maneuver that's more impressive than the quick stop. You'll practice the quick stop or rapid deceleration for a variety of reasons. One, it's an excellent coordination exercise. A good quick stop requires a high degree of coordination of all the flight controls, cyclic, collective, throttle, and anti-torque pedals, in a constantly changing flight situation. Two, you may find yourself in a situation where you'll literally need to put on the brakes. You might be air taxiing across the airport when all of a sudden another aircraft cuts in front of you. Knowing how to stop quickly and smoothly could make the difference between a close one and a pileup. 3. The quick stop is very similar to the flare portion of an auto rotation. If you're knowledgeable and practiced in quick stops, the chances are better that you'll perform a safe auto rotation when it counts. To initiate a quick stop, apply aft cyclic while lowering the collective and applying right anti-torque pedal. Aft cyclic slows the aircraft, lowering the collective prevents the aircraft from climbing, and right anti-torque pedal maintains constant heading. Notice that we're reducing airspeed while holding altitude. Coordination between cyclic and collective must be precise. Applying aft cyclic too quickly or lowering the collective too slowly will result in a sudden gain in altitude, or what's called ballooning. Applying aft cyclic too slowly or lowering the collective too much will result in a descent. Of course, we're maintaining RPM and heading control throughout the maneuver. During the entry to a quick stop, the rotor RPM will tend to increase because of the overall greater angle of attack of the rotor disc. Conversely, the rotor RPM will tend to decrease during the completion of the maneuver because of a lessening of the angle of attack. In fact, you should always watch for a decrease in rotor RPM whenever pushing over from a nose-high attitude, like a steep climb. Once the helicopter has slowed to the desired ground speed, apply forward cyclic to level the aircraft, increase collective pitch enough to prevent or slow the descent, and apply left pedal to maintain heading. A word about safety. Quick stop should only be practiced at an altitude that will permit a safe clearance between the tail rotor and the surface. This varies with the type of helicopter, but the altitude at completion should be no higher than the maximum safe hovering altitude prescribed by the manufacturer. If flying only involved traveling from airport to airport, all we'd really need would be airplanes. However, the unique capabilities of rotorcraft permits us to take off and land in all sorts of places: city centers, mountain clearings, parking lots. To operate safely among buildings, trees, power lines, and so on, the pilot typically follows a confined area procedure. A confined area is defined as any area where flight is limited by obstructions in one or more directions. First, perform a high reconnaissance to determine the suitability of the area for landing. This includes determining wind direction and speed, estimating the type and height of obstructions, and assessing other potential hazards. If the high recon suggests that the area is suitable, you should then fly a practice approach to the landing area. Use this low reconnaissance to verify the information gathered in the high reconnaissance. If everything still looks good on the low recon, simply continue on in on final approach. However, if the situation all of a sudden presents new difficulties, execute a go-around from the low recon immediately. Operate the aircraft as close as possible to its normal capabilities. Don't approach any steeper than you have to. Likewise, when departing a confined area, use a normal takeoff from a hover when conditions permit. Obviously, you have to exercise care when operating the helicopter in a confined area. You must be aware of rotor clearances, turbulence, and other such hazards. Use caution when approaching to and departing from a confined area. Plan the flight path as much as possible to take the aircraft over areas suitable for a forced landing, angling into the wind if necessary. These same considerations apply to pinnacles and ridgelines also. A pinnacle is any area that drops away on one or more sides. Typically, we think of mountaintops and ridges, oil platforms, and rooftop heliports. But even landing on a sidewalk with a curb qualifies as a pinnacle operation. Remember this rule of thumb: if the helicopter can fall off it, it's a pinnacle. Give special attention to wind direction and velocity. If you approach from the lee side, do it with caution. Typically, downdrafts and turbulence will make it difficult, if not impossible, to climb up to the pinnacle landing area. The updrafts on the windward side, on the other hand, can be beneficial in carrying the aircraft up to the pinnacle. If you must climb to a pinnacle or ridgeline, do it on the upwind side for this reason. You'll often find tricky winds on rooftop heliports. The location and proximity of buildings, bridges, and other obstacles creates winds whose direction and turbulence can change dramatically in just a few feet. Some rooftop heliports even have 2 windsocks, one each at opposite corners. If downdrafts and turbulence are expected during a pinnacle approach to a rooftop heliport, plan to make a steeper than normal approach. Use the collective to maintain the desired descent angle. This approach technique reduces the chance that a sudden downdraft might push the aircraft too low. Most people are not aware of it, but helicopters are not very good at dealing with sloping terrain. In fact, many students find slope operations among the most challenging maneuvers to learn in a helicopter. Under most circumstances, you should position the helicopter across the slope and into the wind for landing. When parallel to the slope, slowly lower the collective pitch to start a descent. As the upslope skid touches the ground, apply increasing pressure on the cyclic pitch control towards the slope to hold the uphill skid against the slope. This helps you maintain a fixed position without any forward, aft, or downslope movement. Continue to apply downward pressure on the collective pitch control to lower the downslope skid to the ground. Use the anti-torque pedals to maintain a constant heading throughout the entire maneuver. Maintain normal RPM until the full weight of the aircraft is on the skids, in case you need to make an immediate takeoff due to unstable ground or a slope that's too steep. How steep is too steep? Well, positioned parallel to the slope, the amount of lateral cyclic displacement is limited. The stick can only be moved to the left and right only so far. And the subsequent tilt of the rotor disc can also only go so far. Pushed further, and the rotor hub will begin to hit the rotor mast, a hazard called mast bumping or droop stop pounding. A telltale vibration informs the pilot that the aircraft has exceeded its slope capability. Abort immediately and select a new, less steep landing site. Consequently, the amount of lateral cyclic travel available determines the steepness of the slope on which a helicopter can land. Most helicopters are not designed for operations on slopes greater than about 5 degrees, not very steep. Takeoff from a slope is basically the reverse of a landing. Check that the RPM is in the normal range, then move the cyclic away from neutral and into the slope so that the rotor disc is parallel with the natural horizon. Slowly raise the collective so that the downslope skid begins to rise. As you do so, coordinate cyclic movement back towards neutral, keeping the rotor disc parallel to the horizon. Bring the helicopter to a level attitude before completely leaving the ground. Again, use the anti-torque pedals to maintain a constant heading. Hover momentarily, then move sideways away from the slope. Never turn the tail towards the slope. You'll be risking a tail rotor strike. Another fact that most people don't know is that helicopters, even those with skids, are capable of running along the ground for takeoff and landing at speeds up to 20 miles per hour. Use a running takeoff when high weight or high density altitude prevents a sustained hover at normal hovering altitude. Don't attempt a running takeoff unless the helicopter can hover at least momentarily, because performance will be unpredictable and there may not be enough power to safely get the aircraft off the ground. To perform a running takeoff, head the aircraft into the wind, adjust the throttle in the normal range, and press the cyclic slightly forward. Raise the collective slowly to accelerate into forward motion. Maintain ground track with the cyclic and heading with the anti-torque pedals. This becomes especially critical in a crosswind. At the onset of effective translational lift, apply slide aft cyclic to raise the helicopter off the ground. Maintain a level attitude and accelerate through ground effect, less than 10 feet above the ground, until the airspeed approaches normal climb-out speed and a climb is established. The approach to a running landing is shallower than normal to take advantage of ground effect and effective translational lift until surface contact is made. Upon entering ground effect, maintain a level attitude and allow the airspeed to bleed off. As the aircraft settles to the surface, press the cyclic slightly forward of neutral to tilt the rotor disc away from the tail boom. Control direction of movement with the cyclic and heading with the anti-torque pedals. Maintain normal RPM during the running landing to ensure adequate directional control until the helicopter comes to a stop. Maintain maximum allowable power. Don't lower the collective until the aircraft has come to a full stop on the ground. However, if some braking action is desired, you can lower the collective cautiously. The dangers usually associated with a running takeoff and running landings include main rotor contact with the tail boom, ground resonance, and difficulty in maintaining directional control. Running takeoffs and running landings require a surface of sufficient length and smoothness and that present no barriers to a shallow climb or approach. We're back in the pilot's lounge to talk about a number of hazards associated with flying helicopters that the airplane pilot never experiences. Among the emergencies unique to rotorcraft are anti-torque system failure, settling with power, ground resonance, and situations requiring autorotation. Let's look at these in more detail. The failure of the anti-torque system will result in a loss of heading control and is a serious matter which must be handled as an emergency. Some indications of anti-torque system failure include unusual medium frequency vibrations or sounds, a pitching motion of the nose, or, while at low speeds, a sudden hard yaw to the right. Some helicopters have a chip warning light that alerts the pilot of an imminent failure. An anti-torque system could fail due to a loss of a tail rotor component, failure of the tail rotor drive, or a failure in the mechanical linkage between the pedals and the tail rotor. If the anti-torque system fails while at a hover, you must react quickly. The torque reaction produced by the relatively high power setting will create a turning motion to the right that builds up rapidly. Close the throttle immediately without varying the collective pitch position to eliminate this turning effect. If the helicopter is allowed to spin much past 90 degrees, the torque effect will become so great that you'll lose control of the aircraft. From this point, follow the procedure for a hovering autorotation. Use the cyclic to stop any sideward or rearward movement and place the helicopter in a level landing attitude prior to touchdown. Raise the collective to cushion the landing, all the while continuing to roll the throttle off into the override position. You don't want the engine to kick back in and start turning the helicopter again. The FAA recommends entering autorotation if an anti-torque failure occurs during forward cruising flight. Keep cyclic control movements to a minimum until all pitching subsides. If sufficient forward speed is maintained, the fuselage remains fairly well streamlined. However, if you attempt a descent at slow speeds, you should expect a continuous turning movement to the left. Maintain directional control primarily with cyclic control, and if necessary, by gently applying throttle momentarily with the needles joined to swing the nose to the right, or decrease the throttle to swing the nose to the left. The best and safest landing technique, terrain permitting, is to land directly into the wind with approximately 20 miles per hour airspeed. The helicopter will turn to the left during the flare and during the subsequent vertical descent. Remember to keep the helicopter as level as possible at ground contact. Settling with power is a hazardous condition in which the helicopter begins to descend or settle in its own rotor downwash. It involves high rates of descent, and the addition of more power produces an even greater rate of descent. Let's see how. You must have 3 flight conditions in order to have settling with power. A near zero airspeed, usually defined as less than 10 miles per hour, a vertical or near vertical rate of descent equal to or greater than 300 feet per minute, and the rotor system must be using some of the available engine power, from 20 to 100%. When you have this combination of conditions, the helicopter is, in a sense, descending in a cylinder of turbulent air. The rotor blades are at a high angle of attack and the inboard portions stall, resulting in a movement of air upwards at the rotor hub. The outer portion of the blades continue to accelerate air downwards, causing a recirculation of air to develop within the rotor system. The stall progresses outward along the rotor blades as the rate of descent increases. Raising the collective pitch increases the angle of attack, which further increases the stall. This, of course, further reduces lift, causing the helicopter to descend even faster, just the opposite of what we want. Some situations conducive to settling with power include a steep power approach with near zero airspeed, attempting to hover out of ground effect at an altitude above the hover ceiling for that aircraft, or attempting to hover out of ground effect without maintaining precise altitude control. Recovery from settling with power requires that the pilot eliminate the conditions that caused it. Apply forward cyclic to increase the airspeed, thereby moving the helicopter out of the cylinder of turbulent air. Since the inboard portions of the main rotor blades are stalled, cyclic control effectiveness will be reduced during the initial portion of the recovery. And remember, your initial impulse, because of the rapid rate of descent, may be to add power. But we now know that this is the wrong thing to do. You must instead lower the collective pitch to reduce the stalling. Ground resonance is a condition in which the main rotor system becomes unbalanced, eventually leading to an uncontrollable pendulum-like oscillation of the aircraft. It's most likely to occur in helicopters equipped with a fully articulated rotor system. Normally the blades in a three-bladed, fully articulated system are spaced 120 degrees apart from one another and are constructed to allow some horizontal movement about the drag hinges. Remember, a fully articulated system must allow the blades to lead and lag to compensate for Coriolis force. When one landing gear of the helicopter strikes the ground first, a shock is transmitted through the fuselage up to the rotor system. This shock may cause the blades straddling the contact point to move closer together, or what is called moving out of phase about the drag hinges. So for example, the spacing might then be 122, 122, and 116 degrees. Then the other landing gear may strike the ground, causing the blades to go even more out of phase, aggravating the imbalance. Because this hazard only occurs from contact with the surface, the aircraft is typically in a low altitude, low airspeed configuration and using a high power setting. Sending lots of power to an out-of-balance rotor system is a surefire way to make the aircraft start shaking violently. Although this hazard is most likely to occur during landing, it can also happen during takeoff, particularly if the pilot is tentative with the collective while light on the skids. If you don't correct the situation immediately, the helicopter will go out of control and crash. If RPM is still in the normal range, take off immediately. This will allow centrifugal force to realign the rotor blades and the resonance will stop. If the RPM is low, say during rotor spin-up, immediately close the throttle and lower the collective pitch fully. Removing power from an unbalanced system eliminates the severe wobbling. One of the most distinctive capabilities of helicopters is their ability to recover from an engine failure in flight by auto-rotating. It's reassuring to know that, if necessary, the rotorcraft can be landed in an area no larger than the diameter of the rotor disc. There are three phases to auto-rotation: the entry phase, the glide phase, and the recovery phase. The entry phase is perhaps the most important. If the entry to an auto-rotation is performed correctly and smoothly, the subsequent phases become much easier. If not, you may find yourself playing catch-up the whole rest of the way down. The first step in the entry phase is to lower the collective pitch control immediately and fully to maintain rotor RPM. Lowering the blade pitch converts the usual downward flow of air through the rotor system to an upward flow of air. The relative wind moving upward through the rotor disc produces a ram effect, which provides sufficient thrust to drive the rotor blades. This maintains rotor RPM throughout the descent. There's no time to waste on this step. If you allow rotor RPM to decay too much, and it'll decay really quickly, all lift will be lost and you will indeed fall like a brick. At the same time that you lower the collective, press the right pedal sufficiently to maintain heading and to prevent yawing to the left. Adjust the cyclic to establish the proper attitude. What's the proper attitude? Whatever gives you the correct glide speed. This is when the second phase starts, the glide. Using appropriate cyclic adjustments, you must establish the proper attitude for best glide speed. You should recall in our discussion of the drag speed chart, this is the speed that presents the least total drag. The flight manual for each make of helicopter will describe the proper glide speed for that aircraft. This speed, typically in the neighborhood of 50 to 60 miles per hour, yields the best combination of greatest glide range with the slowest rate of descent. I want to emphasize how important it is to maintain the proper glide speed. Airspeeds greater than or less than this speed will cause a higher rate of descent. A higher rate of descent will require a greater amount of rotor energy to stop the helicopter and creates a more critical situation. Here are some general considerations to remember while in the glide phase of an autorotation. A glide attitude that is too flat will result in a high rate of descent. This is caused by an airspeed that is too high. Apply aft cyclic to slow the aircraft to the appropriate glide speed, thereby increasing lift and minimizing the rate of descent. Normally, you should use only the cyclic control to make turns during autorotation. Using the anti-torque pedals to assist or speed the turn causes loss of airspeed and downward pitching of the nose, especially when left pedal is used. An increase in rotor RPM and sink rate will also develop. Be sure to maintain rotor RPM in the proper range. If the RPM is too high, raise the collective as necessary to increase drag and slow the rotor system down. If RPM is too low, bank the helicopter to increase the flow of air through the rotor system, speeding it up. When autorotating during high density altitude conditions, high gross weight, or gusty winds, a slightly higher glide speed is recommended because the resulting glide angle will better approximate the glide angle obtained under normal conditions. A general rule of thumb is that for every 1,000 feet of altitude above ground, you can expect only about a half mile of glide range. The last phase is the recovery phase and begins when you're approximately 50 to 100 feet above the surface. Start by applying aft cyclic to initiate a flare. As the rotor tilts backwards, the increased volume of air flowing through the rotor system increases the angle of attack and therefore increases lift. This momentarily slows both the forward speed and the rate of descent of the helicopter. It also will increase rotor RPM initially. However, as the airspeed and rate of descent approach zero, the RPM will again decrease. At this point, apply forward cyclic to place the skids in a level attitude prior to touchdown. Increase collective pitch to further check the descent and cushion the landing, and apply anti-torque pedals as necessary to maintain heading. Some additional right pedal will be required to maintain heading after the initial collective pitch is applied because of the reduction in rotor RPM. Use the cyclic control as necessary to maintain a ground track parallel to the direction of travel. And finally, applying slight forward cyclic is preferable to too much aft cyclic in order to prevent landing on the heels of the skids. After all your hard work getting the helicopter down on the ground in one piece, it would be a shame to finish it off with a tail rotor strike. The FAA expects you to know what the requirements are to qualify for student, private, and commercial certificates. In particular, you should know that an applicant seeking a student pilot certificate with a helicopter rating must be at least 16 years old. An applicant for a private pilot certificate with a helicopter rating must have a minimum of 40 hours of flight instruction and solo flight time in aircraft with at least 15 hours of solo time in helicopters. And an applicant for a commercial pilot certificate with a helicopter rating must have at least 50 hours of helicopter flight time. Note that the total flight time requirement is 150 hours, but 100 of those hours can be in another type of powered aircraft. Helicopters must avoid the flow of fixed-wing traffic. It's that simple and vague. The FAA doesn't get any more specific than that. They don't tell you how to do it. It's simply up to the helicopter pilot to stay out of the way. Typically, helicopters fly the traffic pattern at half the altitude and distance from the runway that airplanes do. For example, 500 feet AGL and 1/4 mile. It's also not unusual for helicopters to fly the opposite of the standard pattern. For example, if a particular runway is left traffic, a helicopter might fly a right pattern. These are the usual ways in which helicopters avoid the flow of fixed-wing traffic. Keep in mind, too, that helicopters will often fly direct to a specific point on the airport and avoid the traffic pattern altogether. There will be times when you'll be operating to and from a public-use helicopter landing area. Look at these 3 diagrams. Which diagram do you think illustrates what you'd most likely see? The recommended marking for a civil-use heliport is a square box with a capital H inside. Incidentally, the letter H in the box is oriented with the intended direction of approach. Be aware that heliport markings that look like diagram 2 are still in use, but a triangle with an H contained within it is obsolete and is slowly being phased out. Prior to approaching such a heliport, you'd probably want to monitor the radio traffic and call ahead with your intentions. The Unicom frequencies normally assigned to heliports are 123.05 and 123.075 MHz. As with all aircraft, the pilot in command of a rotorcraft may deviate from an air traffic control instruction during an emergency and when given priority. However, if requested, the pilot in command must submit a detailed report within 48 hours to the manager of the air traffic control facility. Also, no different from other air traffic is the requirement that helicopters must have 2-way radio capability and a transponder with altitude reporting capability, otherwise known as 4096 code with Mode C, when operating within Class B or Class C airspace. Let's look at some general operating rules. When we speak of a category of aircraft, we mean a grouping of aircraft based on intended use. A restricted category aircraft is certificated for a special purpose, such as aerial spraying or banner towing. It's important to remember that no one may operate a restricted category helicopter carrying property or passengers for compensation or hire. The only time another person may be carried on board a restricted category aircraft is when they're a required crew member, a crew member trainee, or they perform an essential function. While en route over water with passengers aboard, a helicopter is required to be equipped with flotation devices. And finally, a helicopter operating VFR over congested area is required to be operated at least 300 feet above the ground except for takeoffs and landings. Well, that's it. We've covered a lot of territory.